Hey class, so here is another lecture video on chemical reactions and equations. So what we've done previously is kind of the intro lesson on chemical reactions and equations, what they are. Then we had a video on how to balance them, and now we're going to have another lecture on how to classify them. This is the last lesson for chapter 8. So after this we move on to stoichiometry, which is very related to balancing chemical equations. So we're going to keep building on these skills, but this is the last one in chapter 8. And this one is on classifying chemical reactions. So we've learned about a bunch of different ones, or we'll find out we've been learning about a bunch of different ones, and we'll learn how to classify them. And the first one we start with is a synthesis reaction. So synthesis literally means like to create. So it makes sense. A synthesis reaction is a reaction where two or more reactants form a single product. So you've got two parts of your reactants that form together to create one combined part of a product. And I've got a couple examples here before. This is very similar to what we've been working with ionic compounds. We had two ions that would combine to form one ionic compound, and that was a synthesis reaction every time because we had two parts, two separate elements, two separate ions that would form together, and they would form one ionic compound. And we've got two examples. One of them is the combination of potassium and chlorine to form potassium chloride, and then we've got the formation of hydrogen gas and oxygen gas to form water. So you can see there's two reactants that combine together to form one product. If you have one product, if your reaction you're looking at only has one product, we know it's a synthesis reaction. The opposite of a synthesis reaction is a decomposition reaction. So basically just in reverse, a decomp reaction is a reaction where a single reactant breaks down into two or more products. It often requires the input of energy for the reaction to occur because if you have a compound, if you have two substances that are bonded together, like we have right here, shown by A and B, it doesn't want to break apart just by itself usually. So usually there needs to be some energy to break those bonds between our two substances for them to be separated. I've got some examples down below as well. You can see we've got one reactant that splits into two products. And I've got the reverse of that water reaction, of that synthesis reaction of water. And now we see the decomposition reaction of water. Water splitting into hydrogen gas and oxygen gas. And just like with synthesis reactions, if we have only one reactant now for a decomposition reaction, we know it's a decomp reaction if we have one reactant. Next up is a combustion reaction. So a combustion reaction, that's what's happening when things are being burned. It's a combustion reaction happening. So combustion happens when it is a carbon-based compound, and we're going to talk about it as a hydrocarbon with oxygen that yields carbon dioxide and water. So our reactants are a hydrocarbon, and you can tell by the name of that, it's probably going to have hydrogen and it's probably going to have carbon in it with oxygen that yields carbon dioxide and water. And it makes a lot of sense that a combustion reaction, something to do with fire, releases energy to its surroundings. We all know that fire releases energy. And a couple examples, we've got the combination of a hydrocarbon with oxygen to form carbon dioxide and water. So the structure of a combustion reaction is pretty similar all the way through. And again, here we've got a combustion reaction, we've got water, we've got our hydrocarbon, we've got oxygen, and it yields carbon dioxide and water. But depending on the hydrocarbon that we are combusting, it determines how much carbon dioxide and how much water we're going to end up with. And so oxygen is an important part of a combustion reaction. So you guys might have found out in like a cooking class, maybe Chef Beck taught it, how to safely put out like a grease fire. That's not something you want to put water on. That's something that you want to like place a metal pan over, and that'll stop the fire because you are starving or you are suffocating the fire from oxygen. And if there's no oxygen, the reaction cannot occur. You also will see this at home. If you have a candle lit, you can put the cap back on the candle, or you can place a metal sheet over the candle, and that restricts the flow of oxygen. That restricts its supply of oxygen, and the candle cannot burn anymore. And we'll get into we would call oxygen the limiting reactant there. So, but we'll get more into that later. Limiting reactant. Next up is a single displacement reaction. This is the second to last one we're going to go through. A single displacement reaction. This is a reaction where the reactants are a single element and a compound, and the products are a different single element and compound. So that single element, that's a reactant, displaces an atom from the compound. So it kind of moves it out of the way and bonds with the atom that it was previously bonded with. It's very common with ionic compounds because ions can kind of slide in, and they all kind of fill a similar, they all bond in similar ways. Our cations and anions bond in similar ways. So it makes sense that our anions are going to displace other anions, and our cations are going to displace other cations. That's going to make sense in a second. So our examples, I color coded them. It's a little confusing, but I think it'll make sense with an explanation. So we've got zinc, and we've got copper chloride. We've got copper 1 chloride here. We've got copper 2 chloride here. And it yields zinc chloride and copper. So it's a single displacement reaction because this single element and this compound switch spots. This single element becomes part of the compound and kicks out the other part, which now becomes a single element. So zinc kicks out copper, and now zinc is part of the compound and copper is by itself. That was a cation kicking out the other cation because our cation was the single element, so it kicked out the cation. Below, we've got bromine and potassium iodide, and it yields potassium bromide and iodine as the single element. So here we've got the anion kicking the other anion out of the compound. So our compound is potassium iodide. We've got bromine as the single element. Bromine kicks out iodide and bonds with potassium. So it's a single displacement reaction. It makes a little bit more sense when you look at it with A, B's, and C's right here as well. It's basically the single element just kicks out one of the elements in the compound and bonds with it. And last reaction we're going to talk about is a double displacement reaction. So this is a reaction where two compounds exchange ions and form two new compounds. So it's very similar to the single displacement, but now it's compounds basically just switching partners. So the anion and the cation that were bound together basically just switch with the partners of another compound. So A and B were bonded together, and C and D were bonded together here. And after the reaction, it's A and D bonded together, the cation from one bonded with the anion from the other, and vice versa. So it's a double displacement. I color-coded this one as well to show that originally we've got this blue compound, sodium bromide, and we've got this green compound, barium chloride. But after the double displacement reaction, we've got the cation from the blue compound and the anion from the green, and then we've got the cation from the green and the anion from the blue. It's a double displacement reaction. And the last two things we're going to talk about are state symbols. So when we start seeing our equations, we're going to start seeing some letters in parentheses after each substance. What that tells us is the physical state of each substance in that equation. So it's how we would expect to see that substance in real life before we ran that equation or after we ran that equation, ran that reaction. So here we've got sodium bicarbonate, and that's a solid. S is for solid. And it reacts with acetic acid. AQ means it's aqueous. It is dissolved in water. And that yields sodium acetate, which is also aqueous. So it's dissolved in water, plus carbon dioxide in a gas form, and H2O, water, in liquid form. So the state symbols are just going to tell us the physical state that each one of our substances are going to be in. And finally, we've got reaction conditions. So reaction conditions are information that can be placed above our yield arrow to show the conditions that are needed for our reaction to occur, or if our reaction is reversible. And we'll see we've got the normal arrow just means yields, but there's other information that we can put in there to show what we need. So down at the bottom, we've got a reaction, and it says for the reaction to go from left side to right side, in this case, reactants to products, reactants of nitrogen gas and hydrogen gas, we need a temperature of 350 degrees Celsius and a pressure of 250,000 kilopascals. That's a pressure quantity. But it can also be reversible. So if we were to go from right to left, we would need a catalyst for this reaction to go from right to left. And if you guys remember from biology class, a catalyst is something that lowers the activation energy of a reaction. It basically just helps the reaction move forward. And that is the last slide. So I'm going to post a quiz as well. And actually, I'll run through a little bit of the quiz right now to show you guys. It might be a little confusing. So we're going to do a little bit more balancing and bring in some classifying of chemical reactions. So we're going to do a little bit more balancing here, but I changed up the format for answering to make it a little bit easier for me. So basically, I give you an unbalanced equation. I ask you to balance it. These are not too bad of balancing equations, and you tell me what the coefficients are. So the coefficient, I'm going to give you guys multiple choice for each one, but when you balance it, I want you to tell me the coefficient for Cl2, two atoms of chlorine in a molecule form. Is it going to be, and that's this one right here, is it going to be 1, 2, 3, or 4? And that's tell you. And then when it's balanced, tell me what sodium bromide would be. Would it have a coefficient of 1, 2, 3, or 4? You go down there, and then you would tell me, is this reaction a double displacement, synthesis, decomp, single displacement, or combustion? And then that's how it's going to go.